close to wind turbines as we have right now in Israel. And I've been working on a project in the Israeli Meteorological Service in an attempt to change that. As I'm sure you've already heard, in Israel we are trying to establish a wind energy sector, and the government has decided to provide a free and as extensive as possible map or atlas of wind energy potential across all of Israel. The atlas that we came up with has 4 vertical levels at 30, 60, 100, and 150 meters. We did not see a need to go by every 10 meters. Okay, now we can start. We have 4 vertical levels, and a major concern was that it must be free for everyone to use whenever they want on the internet. We will have 28 data maps for each vertical level, so it's around 100 maps total, and we intend to double that in the near future. The audience is mostly policymakers and entrepreneurs and the general public. The big firms have their own atlases and their own professionals doing the siting work, and this atlas is not meant to replace on-site measurements. It's been validated partially with the on-site measurements, but it's not based on measurements, so it's not what you would call bankable. It will be available on the GovMap server, which I'll explain why that's an upside of the atlas. And just like the Korean atlas, it's a 100-meter resolution, though unlike the Korean atlas, it's not a 100-meter resolution with time series. It's using microscale, the European Wind Atlas methodology of downscaling only the wind distribution data. The main products of the atlas are the average wind speed maps and the power density maps, not only annual but also by month, and also detailed wind roses for every grid point. Every 100 meters you have a wind rose showing you not only the frequencies of different wind directions, but also the distribution of wind speed from each sector with 12 sectors. We've also calculated annual energy production, AEP, and capacity factor. In relation to the first lecture of this session, we of course do not take into account losses that are generated by the wind farm. This is of course for a single turbine, and we're assuming a generic 2 megawatt turbine. So for considerably smaller turbines, the losses, the capacity factors may be smaller because the losses are larger. As I said, we intend to double the amount of maps because we also intend to give peak hour wind energy potential. By peak hour here we mean peak consumption hours, so that again policymakers can assess how much of the energy that is available in a certain area is available during the hours of peak consumption and are therefore most useful. And in addition to the maps, there is a vast amount of downloadable data tables. Again, for each data point, each grid point, you can download a data table and then input it into any sort of algorithm you wish to use, such as the algorithms that were discussed earlier that generate a complete assessment of the annual energy output. The method, again, familiar to anyone who's worked with the European Wind Atlas or the new World Wind Atlas that's been published about a week ago. We start with using the 80-kilometer 30-year data from the ERA interim, which is, again, reanalysis, what has been just talking about. This is at 80 kilometer resolution, which is about 1 degree. And then we downscale it using the mesoscale model of Cosmo, first at 7 kilometers, then at 2.8 kilometers, and finally we do the final microscale simulations using the WASP software from RISO DTU at 100 meters. So this is the inputs and outputs of the Atlas. The first input is the Cosmo grid point. Here we can see a certain grid point with mostly northerly, northwesterly winds. This is the distribution. You can see that it follows the Weibull pretty closely. The bars here are actual time series from the Cosmo model, so it's not fitted to the Weibull. And then you have a graph here that shows the Weibull that will be used from this point on. We use the coarse roughness data from the Cosmo model so that we can compensate for it, and the coarse topography, again from the Cosmo model. And then we have the more interesting data. We have 50-meter horizontal resolution and 5-meter vertical resolution topographical data, the DEM, that we get from the Survey of Israel. And we took the land use data, also collected by the Survey of Israel, and attached roughness length values to each land use. And with some post-processing, we created a 100-meter map of roughness overall of Israel. This is what you see here. And the final output, in this example, this is the wind energy potential, the wind power density map. As you can see over all of Israel, it's hard to see in this size, but it's 100-meter resolution. As far as the methods go, one of our issues was automation. We had 4,000 Cosmo grid points over Israel and no access to the RISO software that automates such runs. We did not have the frog food software that was used in the Whirlwind Atlas. So we wrote our own script that calls WASP through Visual Basic. In terms of the data sources, this is the map. This time you can see a bit more of what it actually looks like. This is based on Survey of Israel land use data, so it's not available outside of Israel. The graphical data is not terribly interesting. And those of you familiar with WASP know that it's based on the assumption of neutrally stable atmosphere. Unfortunately, this assumption is not necessarily true. Some would say it's mostly untrue in Israel, at least, but also in other places. But you can account for deviations from the neutrally stable atmosphere in the WASP software using the stability parameters, the heat flux and the inversion. And by setting those parameters empirically, trying out several parameter values and choosing the ones that produce the best validation results, we were able to improve our results of the final Atlas. In terms of overall quality of our Atlas, we can't give a very precise estimate to the errors because we do not have enough high masses to verify against. We know that there are some high mass measurements in Israel, but they're all proprietary data belonging to either the Israeli Electric Corporation or wind energy entrepreneurs or other private sector companies, and we do not have access to them. We ourselves have a Lidl installation which was used to validate several of our assumptions. Because we've been focusing our validation on 10 specific areas in Israel, there is a risk of some overfitting, although the stations that we chose were representative of larger areas and areas which we believe to be representative of areas with high energy potential in Israel. So our atlas is probably not very good in areas with very low winds, but that hopefully won't matter too much because those areas probably don't interest many people. So these are the validation results, just an example of validation results. This is annual data. The light blue lines, or light green, I know, is the actual model result, the Atlas result. The blue lines are our proxies using a combination of mesoscale modeling, 10-meter masts, and leader measurements to create some sort of proxy for high-mast truth. And these are the same data sets for 10 meters. So here we have the 10-meter Atlas output and the 10-meter measurement on ground. As you can see, on 10 meters, there are sometimes quite large errors in some of the validation stations. This is again partially because 10 meters was not our intended use of the Atlas. We did not publish 10-meter results. These results are here because they're what's available in terms of measurements abundantly. In the higher level, the 120 meter, you can see that again there are some errors, but generally the results are pretty good, falling within 10% accuracy. Of course, once you look at wind power, as was said earlier, you have to take into account the third power of the wind. So the errors naturally, even a 10% error can grow into a 30% error in power, but this is just fact of life in this sector. So the limitations, again, this is not bankable, this is not a replacement for a measurement campaign. This is meant as a preliminary tool for zoning, for decision making, for initial project viability assessment, for resource availability assessment, not for going to the bank and taking a several $1 million loan to build a wind turbine. In certain areas, because we're using the microscale model WASP, there can be higher uncertainty, specifically in the rugged terrain. We know that the model has problems there. The advantages are, of course, the high resolution, both of the input topography and input roughness, as well as the output. We have monthly data, which most similar atlases do not, allowing a more in-depth analysis of the advantages of wind farms, knowing when exactly you'll be getting the wind power, not only what is the general annual wind power. And what's very important is that this is all integrated into the GovMap portal, the GovMap site, which allows combining the wind energy maps with other data layers. I will show this in a second. This is a small demonstration of me using the interface. This is on the test servers, so the data is incomplete at the moment. But you can see here the map of all of Israel. We're focusing on northern Israel, which is the area with highest potential, which is at the moment loaded into the test servers. And we're choosing here the applications tab of the site. And we entered into the wind energy application. We can choose the height at which we want data, 30, 60, 100, or 150. We chose 100. We can choose the parameter. At this time, it's the wind speed parameter. We can choose whether we use annual or monthly data. We chose annual. And here we have either we take all day or only peak hours. At this moment, only the all day data is available. later there will be peak hours. Here we have the legend and we have the map. You can see that many of the areas, even the ones that are within the map, are white. White areas simply represent very low wind speeds, below 3.5 meters per second at 100 meters. We decided to color them white so as to show that there is absolutely no potential here. Look elsewhere. But in the Golan, we can see oranges and yellows that represent higher wind speeds. This is a power density map. The purples are 500 or 600 watt per meter squared. This does not take into account the elevation, so you need to account for elevation. This will result in several percent less power density because the air density is lower, so the power density is necessarily lower. Here we have a capacity factor map. I'll pause this for a second because I'm not keeping up. The capacity factor has been calculated using the 2 megawatt 100 meter hub height turbine. And what? And this is in percent, starting from 20 to 25 in the green areas. The blues are 30 to 40, and the purples are 45 to 60. Right? So you can see that there are quite a few areas with very high capacity factors for even those medium-sized turbines or medium-large-sized turbines of 2 megawatt. Again, of course, every turbine has its own response function, so it will have a different capacity factor. This is only a sampling to have an idea. Again, mostly for policymakers. You can see that not only in the Golan, also in Galilee, we have quite high potential, above 45% capacity factor. Of course, this is the top of Har Meron, if I'm not mistaken, so unlikely you'll be allowed to build there, but we'll talk about that in a second. Once you click on some point, you can also see more detailed data. You can see the exact values of all the parameters. For example, here you have the A and K parameters under the Weibull assumption. And this is the windrows. Again, we clicked on the top of mountains, so we have all reds, very high wind speeds. But in other areas, you have other wind speeds. You can see here from one look, not only the directional distribution, also the wind speed distribution. And this again changes every 100 meters, depending on where you click. Now, you can also look at data layers near the applications tab. And one second, I skipped it already. The data layers allow us to put another data layer that does not have anything to do with our work from the GovMap portal on top of the wind data. No, this is not exactly that. You can also change the background map. Instead of looking at a map that has topography as the background, you can look at buildings as the background or roads. But you can also add many different data layers. I'd like to go back for 1 second.
I think we are done already.
Really?
The time.
But you didn't give me a notice. I feel cheated. The idea is that this portal has many different data layers, such as nature reserves, such as zoning data regarding both current land use and future intended land use. It has data regarding roads, electricity infrastructure, etc.
Thank you very much.
Thank you very much.